And so this is actually, I should change the circles, day 2, because we did circle equations a while ago. So we took that out of this unit. But we're going to look at how to use the segments involved in intersecting lines to solve problems and those ratios and relationships, which are really kind of cool. But there's 3 segments involved in these. There's your secant segment. Remember, a secant goes through a triangle and has intersects it twice. So that's a secant segment. Your external segment is this portion of that secant segment, this section that's outside, and it's connected. And then your tangent segment, which, remember, a tangent touches the circle only once. So this one is a tangent segment. So there's 3 segments, and those create different ratios in the triangle. So a segment of chords theorem is if you have 2 chords that intersect in the interior of a circle, then the product of the lengths of the segments of one chord equals to the product of the segments of the other. So that's a mouthful. But what that means is if we have 2 secant segments, or 2 chords that intersect here, A to E, this section here, times E to C times the longer section of that same one is equal to B to E times, again, that piece of the same one, E to D. So you multiply essentially the pieces of each segment together, and you can use that then to find, and then they are equal. All right, these products are equal to each other, and you can use that to then solve problems. And so we have here, to find the value of x, we're going to take 4 times x, because we want AE times EC is equal to BE, so 5 times 8. So this one times this one. Okay, and I'm just getting that straight from here, BE to ED. So 4x is equal to 40, and x equals 10. All right, and you solve that out. So that one was the basic concept. It can get a little more complicated than that, as you can see here. And so we have our short length here in this section and this section of this chord. So we have x times x plus 4, because we're going to have here in this one kn times nj, which will equal then mn times nl. And remember, order doesn't matter with multiplication, so it doesn't matter which one of these goes first. So we have x plus 2 times x plus 1. All right, so on both sides here, we're going to distribute. And so on the right side, make sure you're foiling. We have x squared plus 4x is equal to, we have x squared plus x, and then we have 2x plus 2. Well, anytime you have the same thing on both sides of your equation, that cancels out. So if we subtracted x squared over, it just goes to 0. So then we end up with 4x is equal to 3x, because I'm going to go ahead and combine these, plus 2. So subtract 3x, and x is equal to 2. Make sure, though, you're answering the question, because this says to find the length of ML, which is this whole thing, and the length of KJ. Well, they're the same, so we really only need to find the length of one of them to have the length of the other. But we do need to plug in our 2 here to figure that out. So that's 2 plus 4, so that's 6. So 2 and 6 kj equals 8. ml also equals 8, but we can check that here. 2 plus 2 is 4. 2 plus 1 is 3. So this is telling me that ml is 7. So we have a problem here because they should be equal. No, sorry, I'm getting my theorems mixed up. The products are equal. Their sums are not, so we're good. So 4 times, what was that length? 4 times 3 is 12, and then 2 times 6 is 12. Their products are equal, so we're good. So kj is 8, ml is 7. There's a lot of little numbers in there, so if you need to write out those over here instead, then do so. So kj is 2 plus 2 plus 4. ml was 2 plus 2 plus 2 plus 1. All right, so if two secant segments, so again, one side to the next, share the same endpoint outside the circle, then the product of the length of one secant segment and its external segment is equal to the product of the other secant and its external segment. Okay, so this is going to look something like this, where we have two secant segments that extend outside the circle. And I'll tell you what all this means. So we're looking here at the secant segments and the product of these two, so EA and EB. So the product of this small section and then the whole thing is equal to the product of the same thing over here. We have this small section times the whole thing. All right, and so then we can again use that to solve for x. So over here, make sure you're not using just the pieces like we did with the last theorem. So this whole thing is 5 plus 7, which is 12. This whole thing is x plus 4. All right, so the only reason that these are labeled inside is to give you an idea of what the whole thing is. So to set this problem up, we have 5 times 12, not 5 times 7. And then we have that is equal to x times x plus 4. All right, so this is 60 is equal to x squared plus 4x. This is a quadratic. It's been a while since we've solved one of those, but you want to get it set to 0. So we're going to subtract 60 from both sides, and we end up with x squared plus 4x minus 60 equals 0. And that is actually going to unfoil. So to get a trinomial, we had to have two binomials, so two things that look like this. And so we want to know what will multiply to negative 60 and then add to our middle term here, which is 4. And so we just start listing out some factors of 60. So, well, we know that 6 and 10. Well, right away, if this 6 is negative, this adds to 4. If you don't get it on the first try, you could keep going. We know that 2 goes in 30 times, but we can see that only if that 2 is negative, that only adds to 28. Okay, so you just list them out until you find that pair. Well, for this one, once I have that pair, I just need to split this up into two sets of parentheses. So I have x minus 6 and x plus 10 is equal to 0. So if x minus 6 is the one that is 0, because remember, anything times anything, one of them is 0. So x equals 6. Over here, x plus 10 would equal 0, so x could also be negative 10. But since we're talking about length, it can't be a negative. And so x is equal to 6. Okay, that's probably the most complex you'll get because it involves factoring, but that idea stays the same throughout. And so like this one tells you over here that ED, this whole thing, is 12. It just doesn't have it labeled. And A to E, this whole thing, is 8. And so we can once again set up our problem to solve it like that. So we have 8 times x plus 4, or equals, excuse me, 4 times 12. So 8x is equal to 48, and x equals 6. All right, and then last theorem, segments of secants and tangents theorem. If a tangent segment, so remember that's the one that only touches it once, and a secant segment share an external point, so this would be like the very first image that we saw, of a circle, then the product of the lengths of the secant and its external segments equals the square, so we're going to square something, of the length of the tangent segment. So for example, in this image, what all of this paragraph means is that if we take this whole thing and multiply it by the external segment, HK, it will equal the whole length of the tangent one, K to J, times itself. So like KJ times KJ. So we just square it. Okay. So we can set that up like this. So again, we have this whole thing is 8, so we're going to use that. So 2 times 8, or 8 times 2, is equal to x squared, because it's x times x. So 16 is equal to x squared. To get rid of a square, you square root, and x is equal to 4. All right, and one more time. We have this whole thing, and then we have our external and the whole thing. So remember, the whole thing here is x plus 3x, which is 4x. So we're going to set this up as 4x times x is equal to 10 squared. So 4x squared is equal to 100. Don't square root yet. Go ahead and divide by 4 and isolate that variable. So x squared is 25. Now you can square root, and x equals 5. Okay, and that is it. Following the notes is the practice problems, so go ahead and run through those. And that will wrap up our little mini unit on circles. And so we will take a quick like mini test, more of a quiz over this stuff this week, and move on to area and volume. So have a good day.